Okay, welcome back everyone to our afternoon session. It is my pleasure to introduce Gary Greaves, who will be teaching us about Equiangular lines, like this topic. So please, Gary, go ahead.
Thank you, Gabriel. So I am going to tell you about equiangular lines, and I'll start by giving a definition of what we mean by a set of equiangular lines. So we have a set X formed of a bunch of lines spanned by some vectors, which I'll denote by ui. So let's say we have n of them, and we call this a set of equiangular lines if, so we call this equiangular if the following two things happen. So the spanning vectors are all unit vectors. So let's introduce J, and the inner product or dot product between any pair of these spanning vectors is equal to plus or minus alpha, and alpha is called the common angle. So this is the main definition of the whole course. The course will be quite focused, and we'll usually or always be worried about these equiangular line sets. And here, this is just the usual dot product. So just ui transpose times uj. This is our main definition. So we can continue by giving some examples. I think this one doesn't move. Okay, so I didn't plan this very well. And now I have to cover up the main definition. Okay. So examples, if we go in 2 dimensions, then what you can do is carefully draw a regular hexagon around the origin, and then you join all the antipodes to the corresponding, each vertex to its corresponding antipode. And there you have 3 lines, and you can check the angle between any pair of these lines, and you'll see that it's always the same. Okay, so we have one example in 2 dimensions, and here, if you work it out, you'll find that the common angle alpha is 1/2. We can go to 3 dimensions and use another geometric object, very famous, use the antipodes of an icosahedron. So this is where I want to show you a slide. I think my slides are not here. Oh, I should go here. Okay, nice. So I just reveal it by moving this down. So here is an icosahedron, and you can see that each vertex is joined to its corresponding antipode. And you can also, if you like, think of it in another way. So we can just take some vector 1 over square root golden ratio plus 2 with entries golden ratio plus or minus 1, 0. This is just one vector, but we can take permutations of this vector. So you just take all the cyclic permutations of this, and that will give you 6 equiangular lines in 3 dimensions. And here, the common angle is just 1 over square root 5. Okay, so we have 6 equiangular lines in dimension 3, 3 equiangular lines in dimension 2, and one more example I can show you. So we're going to jump for some reason to 7 dimensions, since there's also quite a nice construction. And here you take all permutations. So these are entry permutations, some special vector. Well, again, we'll just call it v, 1 over square root 24, just to make it a unit vector, and then 3, 3, minus 1, 6 times. Take all permutations of this, and then these unit vectors will span 28 lines. And here, the common angle is 1 over 3. So here's just 3 nice examples of equiangular lines. Oh, there's a question? Okay, yeah, so I was anticipating such a question. So you see that all of these vectors are orthogonal to the all ones vector, so they live in some 7-dimensional subspace of R8. So we have 3 examples, and now I can tell you about the main problem of this talk, or of this whole course, in fact. So the main problem what we want to think about is if we're given some dimension d. So we start off with some dimension d, so for example 7. We want to find the largest possible number of equiangular lines in R to the d. So find n of d, which is the largest n, such that there exists n equiangular lines in R to the d. So this is our main problem. And so now I can talk about the aim of this course, which brings me over to a table that I drew earlier. So the aim of the course is to understand how we get this table. We want to figure out how do we know that n of d is equal to these things here. So I claim that we know the answer all the way up to dimension 17. Dimension 18, we know that we can get at least 57 and at most 59. And 19 and 20 also, there's a bit of a gap in our knowledge. And then 21 up to 23, we also know exactly what n of d is. And so today, hopefully I'll get through the introduction to this problem. And I'll tell you about general upper bounds, general lower bounds. And using the general upper and lower bounds, we can convince ourselves that a lot of these numbers are in fact right. The second part, which I'll probably do tomorrow and Wednesday, it will be about enumerating. Is this high enough with the camera?
Yes.
Okay, enumerating candidates. Bit of a mysterious name, but hopefully it will become clear. The last part will be about eliminating the candidates. So this is the overview of this course. And by the end of the course, I hope you'll have some understanding of how we can figure these numbers out. Okay, so first I want to tell you about the main tool that we use to study equiangular line systems. So let me go back to this slide. So maybe I'll just write over here first. So our main tool is something called a Seidel matrix. So here we start off with an equiangular line system spanned by our unit vectors u1 up to un. And we can associate to this something called a Seidel matrix, which is a bit like a gram matrix. So we can put our vectors as the columns of some matrix we call B. Then form the gram matrix B transpose B. And it looks quite nice, the gram matrix, because these are all unit vectors. So the diagonal entries are all ones. And because it's equiangular, the off-diagonal entries are all just equal to plus or minus alpha. So it looks nice, but we want to make it look a bit nicer. So what we do is a slight modification of this. And so I define this S as a Seidel matrix, which depends on X. So this is simply the gram matrix. And we minus the identity to get 0 on the diagonal. And then we divide by alpha. So all the off-diagonal entries are plus or minus 1. And now if I want to divide by alpha, then I should make sure that alpha is not 0. So I can just throw away the alpha equals 0 case. This I claim is boring. It's just orthonormal bases. And I'm going to assume that the rank of B is equal to D, just so I know where these things live. And if I do that, then I can extract some information about the spectrum of the Seidel matrix. So here we have a positive semi-definite gram matrix, and the nullity is just n minus d. And so when we take the Seidel matrix, we find that the smallest eigenvalue, lambda min of S, is equal to minus 1 over alpha because of this, and we know the multiplicity is equal to n minus d. And we can reverse this process. So if we start off with a Seidel matrix, we can extract an equiangular line system. So studying equiangular lines just comes down to studying Seidel matrices. All right, so now we've introduced our main tool. The next thing I want to do is tell you about some general bounds, so upper and lower bounds. I'll first tell you about some upper bounds. So the upper bounds I want to prove first are the absolute and relative bounds. And so I'm going to first talk about the relative bound, since it's easier to prove, I suppose. And so what the relative bound does is it says, well, if you have n equiangular lines in R to the D with common angle, so here we're not just fixing D, but we're also imposing a particular angle, then we know that n is at most D times 1 minus alpha squared over 1 minus D alpha squared. And one assumption I forgot is that we need to assume D strictly less than 1 over alpha squared. It's important when we divide by this denominator, we don't want to flip our inequality. And even stronger than that is when we have equality, then our Seidel matrix just has 2 eigenvalues, spectrum Sx, and we can write out what they are. That's just minus square root d n minus 1 over n minus d, multiplicity n minus d, and square root n minus d times n minus 1 over d, multiplicity d. So this is my notation for the spectrum. I just write the eigenvalues and put them in square brackets, and multiplicity is the exponent. So relative bound is quite useful because it says if you fix d and alpha and you have this condition, then the best system of equiangular lines will have a Seidel matrix with just 2 distinct eigenvalues. This relative bound is essentially just Cauchy-Schwarz. To prove this, well, we know that the smallest eigenvalue of the corresponding Seidel matrix is just minus 1 over alpha with multiplicity. Multiplicity is n minus d. And so we'll just give names to the other eigenvalues. So the ones that's not the smallest, so let lambda 1 up to lambda d be the other eigenvalues. There should be d other eigenvalues, since this has multiplicity n minus d, be the other eigenvalues. So now we can apply Cauchy-Schwarz. So what does Cauchy-Schwarz tell us? It says, well, if we take the sum of lambda I goes from 1 to d, and square it, then that's at most d times the sum of the squares of these eigenvalues. Cauchy-Schwarz. And now we just need to use some property of Seidel matrices. Important proposition about Seidel matrices, let's call it proposition 1, is the trace of S is 0, because Seidel matrices have 0 diagonal, and the trace of S squared is n times n minus 1, because all the other all the other entries are plus or minus 1. So when I square it, the diagonal entries will just be n minus 1. I take the trace as n of them, so I get n times n minus 1. And now we have these 2 formulae for the trace. And here I have some eigenvalues and some of squares of eigenvalues. And so they're almost the trace, but I've taken out one of the eigenvalues here. So if I apply proposition 1, this thing here, sum of lambda I, well, if I add on the contribution from the smallest eigenvalue, I get 0. So inside here is just minus lambda 0. Let's say lambda 0 times n minus d. And if I square that, I'll get lambda 0 squared times n minus d squared. And then that's at most d times the sum of the squares. This time I have an n minus 1, and then minus the contribution from this one. So that gives me n times n minus 1 minus lambda 0 squared n minus d. And then to get this band that we want, we just need to simplify this inequality. So let's go over here. You can manipulate this yourself, and you'll end up with n times lambda 0 squared minus d is at most d lambda squared minus 1. And now, because d is at most 1 over alpha squared, this thing here is just equal to 1 over alpha squared. And so we can divide both sides by this, since this will be positive. So this becomes d lambda 0 squared minus 1 divided by lambda 0 squared minus d. And so this is the bound. If you want to get the alphas, you just use this substitution here. And then the case of equality in this band, since this band is just Cauchy-Schwarz, case of equality corresponds to equality in Cauchy-Schwarz, which means all of these lambda i's must be equal. So equality means that lambda 1 equals lambda 2, and so on, up to lambda d, which is equal to minus lambda 0 n minus d by d, since there's d of them. And this is just n minus d over d alpha. And equality here also tells us that alpha is n minus d over d times n minus 1. And so this tells us exactly the smallest eigenvalue. And so we get these two distinct eigenvalues. All of the lambda I from 1 to d is this one, and the smallest is this one. Okay, so that's the relative bound. And this, we'll see, will be very useful. And we also have the so-called absolute bound, where we can get a bound and we don't care what, okay, some comic relief. And we don't care what alpha is. So next, general upper bound, absolute bound. So by the way, these bands date back to the 1960s/70s, and this one is attributed to Gerson, even though he wasn't one of the authors of the paper that it appeared in. And the absolute bound tells us that n of d is at most d plus 1 choose 2. And if we have equality, then that implies that, again, the Seidel matrix has just two distinct eigenvalues. This time minus square root d plus 2, d minus 1 over 2, and d minus 1 over 2 square root d plus 2. So maybe a lot of you have already seen a proof of this, since it's in Gotzel Royal's book. And so I want to just give a proof in a way you might not have seen it before, in the style of Korn-Winder. So this is going to be a Korn-Winder style proof. So again, we start off with a bunch of equiangular lines, u1 up to u sub n. And common angle is alpha. And so the trick here is to define a bunch of polynomials, f sub I x, in the following way. So this is going to be the dot product of u sub I with x squared minus alpha squared, the sum of squares of the elements of x. So we get one polynomial for each of our unit spanning vectors. And these polynomials have very particular form. So you can see that they're all degree 2, they're all homogeneous, and they all have d variables. So each f sub I degree 2, homogeneous, and has d variables. And so they all live in a particular vector space of such polynomials. And that vector space has dimension d plus 1 choose 2. D plus 1 choose 2. And so therefore it suffices to show that each of these fi, or these fi, form a linear independent set. So we just need to show that these polynomials are linearly independent. So it suffices to show the f sub I are linearly independent. And so we do that in the standard way. So we just want to suppose that some linear combination gives you 0. So let's call that star. And we're going to use some nice properties of these polynomials. So we can think about what happens to these polynomials when we substitute in the unit vectors. So there's a couple of properties. So first property is that if I substitute in u sub j into f of I, then I should get just 0. Why is that? Well, the inner product of any two distinct, so here I is not equal to j. So u sub I inner product u sub j will give me plus or minus alpha. I square it, I'll get alpha squared. And then I minus the inner product of u sub j with itself, which is just 1. So I get 0 if I substitute in uj into f of I. And if I substitute in the corresponding unit vector, then I'll get 1 minus alpha squared. So using these two properties, we can substitute in u sub I into star. And that tells us that ci 1 minus alpha squared equals 0, which implies that ci equals 0. So just plugging them in using these properties, we'll get this, which implies this. And so therefore, these polynomials are all linearly independent. To get equality, so I think I'll skip the details for this one. But the trick is, in the case of equality, the polynomials give you a basis for this space. So in particular, you can write the sum of squares as some linear combination. And of these polynomials. Okay, so you just do some substitution and you'll show that you have equality in the relative band, and then you get two eigenvalues just like that. Okay, so that's a couple of upper bounds. So now we have some upper bounds. The natural question is, can we always get the upper bounds? By the way, I put this link up because you can find the notes.
There is .sg after.
Oh yeah, sorry, .sg. Fine. Okay. Yeah, so .sg, or you can just search for my name on Google, and then crm.pdf. You can find the notes there, or they're also on the workshop schedule, I think. So there's more details there if you like. So now we're thinking, when can we achieve these upper bounds? And so we've already seen some examples of this. So when do we get n of d equals d plus 1 choose 2? Since we know this is the best we can ever do, it's the absolute bound after all. Well, we can do this when d equals 2, that's from the hexagon, 3 from the icosahedron, 7, that was the construction I gave, and also you can do it in dimension 23, which I'll show later on. And in fact, it's widely believed that this is the only time you can get equality here. And so if you do a bit more investigation, you'll find that you can get equality in the absolute band. If you have equality in upper band, then it means that d is 2, 3, or d plus 2 is a square of an odd integer. Is square of odd integer. So you can do this by thinking about the eigenvalues you'll get in the case of equality. And so here we have square root d plus 2. Because of the mismatch of multiplicities, you'll see that in all except one case, this needs to be rational. It needs to be odd for some, well, a reason due to Neumann, but I'll prove that later on. But I don't want to prove this explicitly. But anyway, you can check in the notes if you like, but it's not difficult to show this. What is more difficult is to kill off these candidates. So you can now look at all of the d, such that d plus 2 is an odd square, and think, can I get equality for that d? And so this was investigated by Banai Munamasa, who was speaking earlier, and Venkov in 2004, and more recently in 2012. They were investigating this problem, and they showed that you get strict inequality, can't achieve equality in the absolute bound for infinitely many otherwise feasible D satisfying this. So for infinitely many D such that D plus 2 is odd square. So the message I want you to receive here is that it's not easy to get the best possible. This should motivate more on construction. So how well can we do? So now I get on to some constructions.
Maybe if I can interrupt real
Yeah.
quick, adding on.
If you assume,
Well, that it's additional thing,
right.
But then you have to prove it like.
Yes. So Neil Gillespie did some extra assumption and showed that this really is all you can do if you have that extra assumption. Okay, thanks for the comment. So now on to constructions. So I want to keep this table. So what can we do? Well, the first construction I'll mention is a general construction. It's quite powerful. This is due to Duquesne in 2000. And he constructed for all natural t and d equals 3 times 2 to the 2t minus 1 minus 1, that there exists 2 over 9 d plus 1 squared equiangular lines in R to the d. So this is a general construction. And what this tells us is we can always get quadratically many lines for any dimension d. This is essential quadratic general construction. And this comes from an association scheme mentioned in Bill's lecture, the Cameron-Seidel association scheme. So a corollary of this, if we examine this construction a bit further, we can get this general lower bound of 32d squared plus 3 to 8d plus 296 over 1089. So here we have a general quadratic lower bound. We've already seen quadratic upper bounds. So this tells us that we should have about d squared lines in dimension d with some hit with some constant. So that's a general construction. Next, we can look at some more specific constructions. So the first construction, which is the kind of daddy construction, it has lots of children constructions, is the Witt design. So I'm just going to call this inside the Witt design. And so I was going to give a construction, but due to potential timing issues, if I have time at the end, I'll come back to the construction because there's quite a nice construction of this. But I'm just going to say, using something called the Witt design, we can obtain, or it shows us there exists some Seidel matrix W corresponding to 276 lines in dimension 23. So the spectrum of this Seidel matrix has eigenvalues -5 to the 253 and 55 to the 23. So it's in 23 dimensions. And this one is very, very special. And it gives rise to a whole bunch of other best possible equiangular line systems. So directly, it gives you 276 equiangular lines in 23 dimensions. And what you can do is look at principal submatrices of this Seidel matrix, and you'll find really good Seidel matrices inside. So if you look carefully enough, you can find 176 by 176 principal submatrix, which corresponds to 176 equiangular lines in dimension 22. And you can keep going. So you can find 126 equiangular lines in dimension 21, 90 in dimension 20, 72 in dimension 19, 56 in dimension 18, and 48 in dimension 17. So these three all just have two distinct eigenvalues, so they correspond to equality in the relative band. But this 90, 72, 56, these are not special in that sense. They don't just have two distinct eigenvalues. And these ones I'll just highlight. So the first one is due to Taylor. Again, Taylor mentioned in Bill's talk, very interested in constructions coming from algebraic objects. 72 is due to Asher. And then 56, this is a recent, so these are somehow in the 70s, I believe, 1970s. But 56 is a new result due to Lin and Yu. I think let's say 2020 or 2021. And that was a slight improvement of Zelensky's construction, I think the year or 2 years before. 2000, let's just say 2010s, late 2010s. So you might be thinking, okay, so all the best constructions come from this bit design. And the answer is, it's not clear, because we recently found 57 lines. So this brings me to my next slide. So there exists 57 equiangular lines in R to the 18. And I have to do this. And so I can reveal a construction that you probably can't read or see at all. Do I have to click something?
And turn that on.
Okay, so it may come up. You never know. And so this was constructed by looking in integer lattices. And yeah, so this is the columns of this are the vectors that span these 57 lines. And a couple of interesting things are it has 7 distinct eigenvalues, the characteristic polynomial. And we don't know whether or not this is inside the Witt design. So it may or may not be, you may be able to find the corresponding Zyder matrix as a principal submatrix of the Witt design, but we don't know. And we somehow suspect that you can't. But we can prove that you can't get it inside Asher's line. So we know it's not inside this one, but maybe it's inside something a bit higher up. So that's open question, whether or not the Witt design really is the be-all and end-all of small dimensions. And some more constructions I want to tell you about briefly come from strongly regular graphs. So I don't really want to go too much into the theory of this, since this is quite well studied. So I'll simply say that, I'll simply give a lemma. So if you let gamma be simple connected k-regular graph, k-regular graph with eigenvalues, you need 2 hands for this board, k bigger than lambda 2, at least lambda 3, and so on. Then what you can do is turn this regular graph into a Zyder matrix. So you can say S is equal to J minus I minus 2 times A. So the adjacency matrix here is just A. Then this is a Zyder matrix, and the eigenvalues are easy to work out from these eigenvalues. So you get n minus 1 minus 2k, and minus 1 minus 2 lambda I for all I at least 2. So going from regular graphs to Seidel matrices, you can easily work out their eigenvalues. And so we can show you the following table, which gives us a whole bunch of equiangular line systems, which just come from known strongly regular graphs. So you'll see some familiar numbers there coming up, and you can go down to dimension 5 if you like, which is this Peterson graph. Peterson graph showing up is always quite promising for any particular field of study. And so as a corollary, I'm going to mention a bit of a strange corollary to all of these constructions. So corollary I want to mention, so if you analyze these constructions, what you can say is that for D at least 6, for all dimensions at least 6, except for 14, the number of equiangular lines is strictly greater than 2 times D. So we already have this quadratic lower bound. Why do I care about this linear lower bound? Well, that's what I'm going to tell you next. So we've seen some upper bounds and we've seen some construction. Now we want to concern ourselves with the question of, is some given construction the best we can do? So how do we prove maximality of a given construction? So the first result I'll mention is due to Neumann, which I loosely mentioned earlier, again from the 70s. So Neumann observed that if there exists n strictly greater than 2d equiangular lines in R to the d, equiangular lines in R to the d, then it tells you that 1 over the common angle is an odd number, an odd integer. So this corollary is kind of giving some power to Neumann's observation. And so because of this observation, it greatly restricts our attention for potential angles or smallest eigenvalues. And so therefore we accordingly define a slight variation of n of d. So we define n of 1 over alpha d to be the maximum n, such that there exists n equiangular lines, in R to the d with common angle alpha. So we have this slightly modified sequence of numbers that we want to study, and this will help us study maximality of particular constructions. So again, there was a lot of stuff in the 70s for this overview. So Lemons and Seidel showed that the dimension is strictly less than 2m plus 1 squared, so some odd number squared. Then the number we're really interested in, n of d, can be bounded above by the maximum of n 3d, n 5d. So you just do all the odd numbers up to 2m plus 1 of d. So this is just really using Neumann's observation, this corollary, and the relative bound. So most of these are just saying that the relative bound, once you can apply it, it just keeps getting smaller and smaller when you make your odd number bigger and bigger. But before, you need to check the odd numbers before you can apply the relative bound. And so this gives us a really nice way of attempting to prove maximality. We just need to focus on these small odd numbers. And so Lemons and Seidel also investigated what happens in this case where the odd number is 3. So Lemons and Seidel, in their seminal paper, again in the 1970s, they showed that n3 of d is equal to 28 for d in 7 up to 15, and 2d minus 1, d at least 15. So this tells us that using 3 as my odd number for my angle, it gets rubbish once d is at least 15. So it's pointless using this if you just get some linear number of lines. So it's completely rubbish. And then very recently, Sao, Colin, Lin, and Yu, so this is 2022, they covered the case where the odd number is 5. And 5 of D, this is equal to 276 for D going from 23 up to 185. And the floor of 3 over 2 D minus 1 when D is at least 185. This is a very recent result, and that deals with the case 5. So it essentially says if your D is at least 185, then you're going to get some rubbish linear upper band. And if you look at this carefully, you only have 2 data points, but you'll see there's a D minus 1 here, a D minus 1 here. So this asymptotic continues as you might hope. And this was a recent celebrated result. Don't want to use that board on the ground anymore. So the asymptotics for odd numbers have been worked out last year. So this is Jiang et al. They showed that n of 2m plus 1 d is equal to the floor of m plus 1 over m d minus 1 for any m natural number and sufficiently large d. D is large enough, then we get this linear number of lines. So to make progress, we want to know how large is sufficiently large. So for these other results, we know how large sufficiently large is, and so we can use these for maximality. This result we can't yet use for maximality, but it at least tells us that the pattern that we would expect continues asymptotically. And so now that's the introductory results dealt with. So now we can actually start getting our hands dirty and trying to prove some maximality. So let's think about n of 2. So we saw at the beginning that we know the lower bound is 3. We know we can get 3 lines in dimension 2. And the absolute bound also gives us 3. And so we know that n of 2 is equal to 3, just using the absolute bound. And the same thing for dimension 3. So we saw we can get 6 lines from icosahedron, and the absolute bound also gives us 6. So these things both follow from the absolute bound. Okay, n of 4. So maybe I should just show you the table at this point for comparison. So you can look over here, see the table. The claim is it's 6. How can you show that? So this doesn't use the absolute bound gives you 10. So the absolute bound is not quite there. So to do this one, I want to leave that as an exercise, since this is a mini course after all. So see if you can figure that one out. But what I will do is figure out n of 5. So how can we show that n of 5 is equal to 10 using the theory we have so far? So the idea is as follows. So let's suppose that you can have 11 lines. So suppose there exists 11 equiangular lines, equiangular r to the 5. So Neumann tells us, says, wait, this is more than 2 times d, so the smallest eigenvalue must be an integer, or 1 over alpha is an odd number. So 1 over alpha is equal to some odd number. Now we can apply the relative bound. So because d is strictly less than 2m plus 1 for all m squared for all m, we can apply the relative bound. So the relative bound, actually, let me move over here. So we can apply relative bound, and it says that n 2m plus 1 of 5 is strictly less than, not strictly less than, at most 5m plus 1 over m squared plus m minus 1. And if you manipulate this, you can write it like this, 5 plus 5 over m squared plus m minus 1. And this is strictly less than 11. So you get a contradiction. Okay, and you can continue this, go to n6 is 16. And the idea is very similar. And then n7 is 28. This is where the absolute band tells us this is the best. And then n with the 8, n of 8 up to n of 13. This is similar to again, similar to above. And this equals 28. So at this point, if we continue to n of 14, we won't be able to show that n of 14 is 28. So if we check n of 14, all we can say at this point, using the theory we have so far, is that it's at most 30. But in our table, you'll see that n of 14 should be 28. And so that motivates what I'm going to talk about for the rest of this course. And so also n of 16 would be at most 42. N of 17 is at most 50. And so for the next 4 lectures, I'm going to try to show you how we can improve these upper bounds to show that the constructions we know about are the best possible. And so if I go back to my plan, which I've already erased, I'm first of all going to think about how do we enumerate all the candidate polynomials that correspond to these large systems of lines. And then the last part, I'm going to show how we can eliminate each of the candidates that we find. Okay, so that's the plan for the rest of the talk. And that's where I'll stop for today. Thanks for your attention. Please ask questions if you have any.
Are there any questions for Gary? I'm going to ask a question.
So where do you think the cutoff is between the small examples and the large examples? Because at some point, the one that you found, their angle is like a fifth.
Yeah.
Right. So there is some point at which Neumeier is bound that they will be equal to some number, some function in terms of D eventually. But there's some space before it hits that. So what do you think?
Yes. Yeah, it will go to 1 over 7 at some point. I think it starts from dimension 43.
So in dimension 42, you can still do better, or what's that?
Yeah, dimension 42 is unknown. We have a gap at 42, so we know all the way up to 41 that 276 is the best. This kind of continues up to dimension 41. And dimension 42, I think it might be possible to get somewhere close to 288. And then from 43, I think you have 344 lines coming from some construction with 1 over alpha is 7. So I believe that would be where the 7 will kick in.
And sorry, when you get a strong regular graph out of them?
Yeah, so I didn't go into the details, but when you have equality in the absolute or relative bound, there's some strongly regular graph hiding around the corner. But even if you don't have equality in the relative bound, sometimes it can still correspond to a strongly regular graph.
Is it by switching off the vertex?
No need to switch off. So in the case where you have 2 distinct eigenvalues for your Seidel matrix, you can always switch some vertex to be isolated, and then the connected part will be a particular strongly regular graph. But you don't have to do that. So you can just take a strongly regular graph that has an eigenvalue of very high multiplicity, and that would be a candidate that would give you a good equiangular line system. It won't necessarily give you equality in the relative band, but it still might be quite good.
This is what Seidel calls regular 2 graph?
A regular 2 graph would be the one that you could switch away.
Oh, okay. So you didn't get a strongly regular graph for the 57?
Yeah, so for the construction I showed, the 57 lines, there's no strongly regular graph associated with bands. It actually, the Seidel matrix has 7 distinct eigenvalues. And we actually have we can construct many different systems that give us 57 lines. It's like then they're really numerous. And we just focused on the ones that had a small number of distinct eigenvalues due to the classical results. But I know from, I don't know if, yeah, maybe I can't publicly say something, but yeah, I know something else about it. But I'm not sure I have permission to divulge.
Yeah, the second neighborhood of Starling regular graph.
Yeah, possible. Well, second neighborhood, wouldn't that just be the complement?
No, the second.
Oh,
neighborhood.
you mean inside the neighborhood? Okay. I don't know. I'm not sure. I haven't checked that.
I think the angle passes from 1/7 to 1/9 to dimension 76, and then I'm just looking at data, and then it passes to 1/11 to dimension 117.
So I mean, basically, this sufficiently large G for all these asymptotic results, is dependent on it.
Yeah.
So like, at the point at which it's leveling out for one, like 2m plus 1, like at that D, then that 2m plus 1 isn't, the reciprocal of it isn't likely to lead to the largest number of equiangular lines. So like where 1/5 bottoms out, we're probably going to be at 1/7 or 1/9 as the largest package. And so it's an interesting result, but like for maximal size, usually it's like 1/3 bottoms out, but then 1/5 is optimal. 1/5 bottoms out, but then 1/7 is optimal. So like there is like a gap between, oh, that's a really small number, but we could get quadratic. The D, yeah, has a this visual largely has a hinge of
Once you're given your D.
Yeah.
Is the angle between the lines determined just from the?
No. In the extremal cases, it is. So if you hit the absolute bound, then you know what the angle is. Otherwise not. But if you go above 2 times D, then you know that 1/alpha must be odd integer. I mean, you can say stronger things actually. So hopefully the next couple of lectures, I'll introduce some more restrictions on the eigenvalues of a Seidel matrix.
You've got a system of equilibrium involving some angle cosine alpha. Okay, and now we bring in another line system that's not actually an equiangular line system, but the minimal angle between 22 lines is also alpha.
Okay.
So if you weaken the, if you replace the assumption of equiangular lines by the requirement that the minimal angle is L, can you affect that more lines into the same dimensional thing?
Well, I would guess so, but I haven't looked into doing anything like that. It's yeah, my investigation has been pretty focused on just equiangular lines.
What might seem to happen is that what's really controlling the ground is essentially the requirement of the middle line versus L. The fact that all the lines have to be alpha alpha, maybe it's not actually used.
Well, the proof I mentioned by Kornwinder, so there's a more general study of where you restrict the number of different angles allowed. So you're allowed, let's say, 2 different angles. Then you'll get a slightly larger upper bound. And I think there's been a recent interest in, for example, biangular lines, where I believe there are larger constructions of such things, but I'm not sure if their restrictions on the angles are the same. I haven't had a look at that.
Oh, you just like you were like. Okay, maybe I'll.
So there is like some work on like, and it's not, I've just seen talks, I haven't read the papers, but like, I want to say it's Frank Valentine, and you look at like a range. So it's like alpha to 1, and there's a continuum of possible angles between alpha and 1 rather than these discrete sets that are more combinatorial. And there is a thing you can do called a topological graph, which is some sort of continuous graph structure. And again, I've only seen like some talks a few years ago and haven't read the papers, but there is some way to use combinatorics to study this more like
continuous version of the problem.
If I take a system of equiangular lines, I want to create a spherical code. So I choose some line, I call it one endpoint, one unit vector to the North Pole, and I take all the other unit vectors that have an acute angle with it. So I get a spherical two-distance set. So there was this outrageous conjecture of Busen, right? That the spherical two-distance sets, the best you can do is midpoints and edges of simplices, except in those dimensions, odd square lines, 2 or 3, I forget. Does that have impact on equiangular lines? That new proof, because they proved you and someone else proved that.
Oh, when was this?
Just a year or two ago. Of Busen, no special dimension. N times n plus 1 over 2, you can do.
Oh, okay, I'm not sure about that.
Yeah, I'll try to pick it up, see if there's something.
Yeah, that would be interesting.
Thank you.
So,
I was curious about that gap between 7 and 14 that you cannot really improve until you go to dimension 15. You mentioned that you prove it, at least for those in particular, with the same type of argument.
Oh, for this one?
Yeah,
Yeah.
and but I also see that it's related to the result by Lemons and Seidel of the angle, the absolute,
so-
the relative bound for
right.
angle 3.
That's true. So in this case, the similar part, there's a small difference, which is that you have to check 3 separately. So yeah, the result of Lemons and Seidel, wherever it is, over here. Yeah, this is really, really useful. So this means that the relative band becomes stronger because you can kind of deal with where it doesn't apply. And then recently this one's come in. So this is opening the door for studying even higher dimensions.
Yeah. So should we expect such a behavior like further on? Like, do you think? that
Yeah,
we'll
I
find
think
out
this behavior
we need
repeats. So
more?
if I had more room,
Hmm.
then this would be 23 up to 41, 276.
Uh-huh.
And then 42, there's a gap. I think I would guess it's this to 288. And then 43, I think that jumps up to 344. And then I'm not sure what happens after that. So I don't know about the general interest of everyone else, but I like to know this continuous sequence up to a point. So we filled in the gap for 14, 16, 17. 18 it seems quite difficult. Yeah, trying to fill these in. So, because if we can solve these, then it will be known all the way up to 41, which is way more impressive than up to 17.
you try to type in 3, 6, 6, 16, Neil Sloan,
Oh yeah, of course. It's one of Neil Sloan's favorite sequences. He sent me an email about it. He actively looks at that page.
That's a really good one.
Yeah, it doesn't give you any insight to other objects or anything. If you type it in, this exact sequence will come up. Okay, it will come up probably up to 17, and then some extra information about higher ones.
There might be a sequence of like the best node upper bound, but it's like a longer version of that.
Oh, I haven't seen that.
There'll be like
Well, I don't think 59 is there. This is very, very new. So
Oh.
this is
So let's go for a break and thank Gary again.